Alright, third time's the charm, hopefully. So let's get back to some problems, and now we're on to this new problem dealing with this fraction. And there's no square roots or anything, and no trig functions involved. So trig substitution, trig integration's out. And now if you look at, you might say, okay, well maybe integration by parts. Well, good luck with that with all those terms down below. What this is screaming to you, first off, let's take a look at x cubed minus 3x squared minus 4x plus 12. If you notice, you can group those first two terms. You get x squared, and then that would become x minus 3. If we do minus 4, notice what do we get? Well, that'd be in x, minus 4 times x would give us that. Minus 4 times what will give us positive 12? Well, it would be minus 3. So just by grouping those terms separately, we get that. So now what happens? Well, we get x squared minus 4, that quantity times x minus 3. And so now we have x squared minus 4, by the way, is a difference of squares. That's x plus 2 and x minus 2. So we can rewrite this, and I'll put a 1 up top just to try and indicate what's happening here. 1 dx equals x minus 2, x plus 2, and x minus 3. That's just from factoring that thing. Okay, so now if that's the factors, we have a partial fraction decomposition that we can try here. So we have 1 over x minus 2, x plus 2, and x minus 3. So notice that this would be a over x minus 2 plus b over x plus 2 plus c over x minus 3. Okay? So keeping that in mind, what do we have to do? Well, you can multiply both sides by that denominator. And what that'll do is that'll leave us with a times, well, first off, the left-hand side I should write, is 1 equals, rather than put it on the other side, a times the quantity x plus 2, x minus 3, plus b times the quantity x minus 2, x minus 3, plus c times the quantity x minus 2, x plus 2. Okay, so if that's the case, where do we go from here? Well, you can start plugging in x values. And so when x equals, in this case, and I see there might be a question that you missed a piece, all we did was factor by grouping. So that's what this was, factoring by grouping. We grouped the first two terms together. So we wrote it as x cubed minus 3x squared. Group those two. And then we go minus, but notice that changes this to 4x minus 12. That's all that happened. And then you can rewrite it in terms of the integral of a factored version. So x minus 2, x plus 2, x minus 3. So that's how you factor this cubic. And then now we were doing our partial fraction decomposition. So the partial fraction decomposition, this is all just algebra at this point. So when x equals, we're plugging in values of x when this thing would equal 0. And so we have, when x equals negative 2, what do we get? Well, notice this first term, it would be 1 equals, on the left-hand side, we get a times 0, plus, b is a little bit more interesting. B equals, we have negative, oh, not b equals, b times, negative 2 minus 2 is negative 4, and negative 2 minus 3 is negative 5. So, and then plus c times, once again, 0. So notice this gives us 1 equals 20b. So that b becomes 1 over 20. Okay, so now we have actually part of our integral when we're writing this thing out. This thing equals I don't know what the first term is. All right, we're going to have an x minus 2, but we do know what the second term is. So when we have x plus 2, we're going to have a 1 over 20 up top there. Okay. We can use that equation a little bit more, and the other one we're going to need is x minus 3, and we can solve all these. They're not too hard. Okay, so moving forward from here, when x equals, well, let's do positive 2. Notice what do we get? We get 1 equals, you get a times 4 times negative 1. And the other two terms are going to be 0. You can plug them in. 2 minus 2 gives you 0, and then another c times 2 minus 2 gives you 0. So all you're left with is 1 equals negative 4a. So that means a equals negative 1/4. Okay? So that means we have a negative 1/4 up in front of that x minus 2. Hopefully that makes sense at that part. And then the last part we have when x equals 3. What happens? Well, when x equals 3, you plug it into the first two terms, you're going to get 0. So you get 1 equals, in that case you'll get c times, well, 3 minus 2 is just 1, and then 3 plus 2 is 5. So we have 1 equals 5c, so c equals 1/5. And so we can put a 1/5 up there. Now the beautiful thing, each of these would be a u substitution if you wanted, a different u substitution, but if you notice, when we take the derivative of x minus, like u equals x minus 2, that means du equals just dx. Each case you aren't having any extra constants appearing there, so there's nothing to worry about in terms of what happens. The only constants that we have to worry about is up top. So our antiderivatives of each of these are going to be natural logs of just that function along with the constant there. So you get negative 1/4 natural log of x minus 2 plus 1/20th natural log of x plus 2 plus 1/5 natural log of x minus 3 plus some constant c. If you have any questions on where those natural logs came from, please let me know. I'll be happy to explain. But in other words, all you're getting to is just that nice little sort of natural log business, because each piece, when you look at this, the x, we don't have anything anything adding to our derivative in any of those cases, because the derivative of that with respect to x is always going to be 1. So that's the reason why. Okay, yeah, so if you have a question, please explain. Okay, yeah, so let's just do the first one, and hopefully we can get the gist. So let's go negative 1/4 x minus 2 dx. So assume we broke that up into different integrals. So now I'll say, let's rewrite this as negative 1/4. Yeah, it's very similar. It's not quite 1 over x, but it's very similar, and I'll explain why. This is 1 over x minus 2 dx, right? So notice you can set u equal to x minus 2, and then that means du equals dx. So in essence, what's happening here is you get negative 1/4 the integral of, you get 1 over u du. So that means this is negative 1/4, and the antiderivative of this thing is just natural log of u. So you get natural log of u plus some constant c. So this thing equals negative 1/4 natural log of x minus 2 plus some constant c. And notice, was anything special about that being x minus 2? If I had changed it to x plus 2 and just moved the other constant out in front, would that be any different? Well, the answer is no. The derivative, the du, will always be dx in each one of these cases. Now, if I had a 2x plus 3, it does become a different sort of scenario, and we'd have to account for that. But since all of them are just x to the first power, and then the leading coefficient in front of that is just a 1, we have every single case is going to be just a natural log, straight across. Now, if it's x squared or something like that, it becomes a totally different scenario. But I want you to be aware of a lot of these you can kind of go through a lot quicker. But if you want to take the time to do substitution, you're more than welcome to. So yeah, and I'm glad you asked. So that's the big thing, is if you have a question, just ask. That's what I'm here to do. So that's the main point. If you ever get stuck on a spot, so some parts like the U substitution, some of them go easy for people, some of them take a little bit more time. I just want to kind of touch on the main concepts of the Calc 2, and if you get stuck on like some of the Calc 1, like just the U substitutions and things like that, let me know and I can brush that up too. So I'm happy to do that. That's what I'm here for, just to try and help overall. So moving to this problem, this one's different than the other one, and notice that you can't factor the denominator, x squared plus 1. If you notice, the only solutions are I and negative I, so this thing can't be factored over the reals. So if you look at this one, how do we actually approach it? Well, it's kind of hard because we have that x cubed plus 1 up there, but we can start to work with that. We're going to divide these two polynomials. So we have x cubed plus 0x squared plus 0x plus 1. We're going to see how much goes into this x squared plus 0x plus 1. So first off, we start with x squared. That goes into x cubed how many times? Well, you need to multiply x squared times x to get into x cubed. So we'll multiply that on through, and that means we get an x cubed plus 0x squared plus, well, x times 1 will give us just 1x. But now we have to subtract those two functions, so we have negative x, and then we have a plus 1. Okay? So notice, though, we can't plug in x squared and divide and get x. We have no x squared terms, so you get 0x squared. So x squared to 0x squared, that'll just be 0. So what this means is this is our quotient up here, and I can drop the 0x squared, and this second component here is our remainder. Now, just like when we do long division, let's say I had 7 dividing into 25. Notice that goes in 3 times, and so we're left with this. So what that means in terms of what happens here, if we had 25 over 7, that would be 3 and 4/7, or a better way for us to write it in terms of what we're trying to do here, that's 3 plus 4/7. Okay? So this integral, in a similar manner, we could write this as x, because that's our quotient, plus, oh, and by the way, I need an integral there, negative x plus 1 over x squared plus 1. And then we have a dx. Now, moving forward from here, what happens? Well, when we take the antiderivative of x, that's going to be pretty easy. That part's going to be 1/2 x squared. Okay? So, but the other components, I'll say, it's going to be a little bit trickier, and we're going to want to break them into separate integrals. So we have x over x squared plus 1 dx, and then plus the integral of 1 over x squared plus 1 dx. Now let's see if we can solve either of these scenarios. So the first case, that's good. This x over x squared plus 1, notice if you let u equal to x squared plus 1, and then you get du equals 2x dx, that means you get du over 2 equals x dx. So you can write that second integral as, well, notice you have a u in the denominator, and then you have a du over 2, essentially, in the numerator, which we'll deal with in a second. And then the third one, that's just the arctangent. So the arctangent derivative you might recognize. So we have solutions there. Now, that du over u business, what happens there? So we can pull the 1/2 out in front, so minus 1/2. Du over u, that's just natural log of u. Oops. Plus, move that back up, arctangent of x plus some constant c. So this equals 1/2 x squared minus 1/2 natural log of, well, this should be x squared plus 1 because that's what u is, plus arctangent plus some constant c. Okay, so hopefully that makes sense. If not, please let me know once again. Be happy to try and elaborate a bit more there. So let's see, going forward, now we'll move on to what's an improper integral. Now, why is this improper? Well, when you plug in 0, you get 0 in the denominator. So this thing's improper, so that means we have to approach it as a limit. So we're going to take the limit as t approaches 0 from the left, or I'm sorry, from the right, except from the left I meant from the right, of, we get t to 1 of e to the square root of x divided by the square root of x. Now, what we might want to do, we'll go back to this, since before we didn't like the bounds right away. We can deal with this as an antiderivative, just a general antiderivative, and find a solution here. If you let u equal to the square root of x, then du equals 1 over 2 square root of x. And the way you can get that is this is x to the 1/2. That's 1/2. X to the negative 1/2 is the derivative, which is 1 over 2 square root of x dx. So notice that 2 du equals 1 over square root of x dx. So moving forward from this part, let's see what happens. Well, you can rewrite this as e to the u, and then you have 2 du. So this thing is 2 times the integral e to the u du, and so that is 2 e to the u plus some constant c. But e to the u was just e to the square root of x, and we have plus some constant c. Okay, so now this thing becomes limit as t approaches 0 from the right, and then we know our antiderivative is 2e to the square root of x, and then you have a t and a 1. So now, moving forward from there, you get limit as t approaches 0 from the right. You get 2e to the square root of 1 minus 2e to the square root of t. Okay, so square root of 1 is just 1, so you get 2e minus, well, 2e to the 0 essentially would be just 2, and then, well, I'll write it here, e to the 0. And so this is 2e minus e to the 0 is 1, so you get 2. And that's your final answer. Okay, great. I'm glad to see a comment about the tutoring. Yeah, there's plenty of tutors around, and if you're meeting with a tutor, that's great. That's awesome. I strongly suggest it. I'll also be in for every time Monday, Friday, unless you see a notice otherwise. You can always stop by my office between 11 and 2. That's a guarantee. Sometimes people will book appointments though as well, so you're more than welcome to stop by during those times. For this week, I will actually also be in Wednesday at 5:30 p.m. I have a meeting from 4 till 5:30 p.m. And so, but you're more than welcome to stop by at 5:30 p.m. and I'll be happy to help you then too. So moving forward now, we're moving into the comparison theorem. Determine whether the following integrals converge or diverge. So how do we approach these things? Well, comparison theorem, if you recall, basically states if we have a function and another function, and say we have some starting point A, if the bottom one's g of x and the top one's f of x. So, and we're going on forever and ever, where g of x is always below f of x. If the integral from a to infinity of f of x dx converges, then the integral from a to infinity of g of x dx converges. Now you can reverse this. You're going to see one that has a 0 and 1, so that might freak you out a little bit. But don't let that fool you. It's still going to work out just nicely. The second case, if the integral from a to infinity of g of x dx, so now the smaller function, if that one diverges, so if the smaller function diverges, then the integral from a to infinity of f of x dx diverges as well. Okay? So now moving forward on this, how do we try and handle this part? Well, notice you have 1 over square root of x minus 1. So think about this, and we start from 9 to infinity. Well, if you plug in 9, notice you get 1/2. So compare that to, say, 1 over square root of x, which would be a much simpler integral. So notice that would be 1/3. Well, which one's bigger, 1/2 or 1/3? Well, notice the 1/2 would be bigger. So you're having this on the interval 9 to infinity. Now let's take a look at the integral from 9 to infinity of 1 over the square root of x dx. Notice that's x to the negative 1/2, right? So the antiderivative, in just an FYI, so if you want to write it this way, you can. X to the negative 1/2, that integral, would be the same thing as you add 1 to each, so you get 2x to the 1/2, or a better way for us to write it so we can visualize it, this is 2, well, actually I forgot to do one thing. Let me write it this way first. I have to talk about a limit since I can't plug in an infinity. Limit as t approaches infinity of 9 to t of 1 over square root of x dx. So this thing equals the limit as t approaches infinity. And some of you might recall from the p-values, you could say that right away and that would do the trick. So this one's 2 square root of x evaluated at 9 and t. But the limit as t approaches infinity of 2 square root of t minus 2 square root of 9, notice that thing's going to equal infinity. So this thing diverges by the comparison theorem. Okay? Because we found something smaller than it that actually diverges. It goes to infinity. So we have a problem there. That's not going to work for us. So in the second one, we got to find a function that works with this one. So now the interval, you have to be careful. It's 0 to 1. It's no longer to infinity. So if we have 1 over x e to the x plus x squared, and we're dealing with 0, 1. So notice this is the same thing as 1 over, if we factor out an x, this would be e to the x plus x. And if you think about 0, 1, what's the maximum this thing can take on here down below? Well, it will be e. If we plug in 1, you get e plus 1. That's the worst case scenario. So this thing is always greater than or equal to, on this interval, 1 over e plus 1 times x. So on, now the key component is, this is on the interval 0 to 1. Well, I should be careful. The 0 is not included because this is an improper integral. So on 0 to 1. Okay, so now let's take a look at the integral from, and let's do the limit as t approaches 0. Of t to 1, and you have 1 over e plus 1 to the x, and then we have a dx. So this antiderivative 1 over e plus 1, that's just a constant. So we'll pull that out in front. You have 1 over x. So that's just natural log of x evaluated at t and 1, and so we need to slap a limit in front of this thing. Limit as t approaches 0. I should put from the right as well. Okay, so this thing becomes the limit as t approaches 0 from the right of 1 over e plus 1 times natural log of 1, which is going to be equal to 0, minus natural log of t. But that's a little bit more interesting. This thing approaches negative infinity then. So minus a negative infinity makes a positive infinity. So what does that mean? Well, we found a smaller integral that diverges. So by the comparison theorem, when I wrote diverges by the comparison theorem, I should write the right appropriate integral, the integral from 9 to infinity of dx over square root of x minus 1. So by the comparison theorem in this case, an integral that didn't look quite like what we solved, the integral from 0 to 1 of dx over x e to the x plus x squared. By that comparison theorem, this thing also diverges. So that's the tricky part, is when you get this comparison theorem, how to work it. But as soon as you figure out what function to work with and compare it to, you're good to go. In understanding those p-series, that's actually very important if you understand those. That can cut down on your time. You don't even have to show the integral that we were working here. So keep that in mind when it comes to your own problems. Okay, so air bounds. Now, these things get a bit tricky at times, but we'll try and work this out as best we can. And I understand you won't have a calculator come exam time, so I'll tell you an appropriate stopping point. But just for kicks, we might try and see how far we can go with this thing. So find n such that Sn has an error of at most 10 to the negative fifth when estimating the integral from 1 to 4 of 1 over x dx, where you have this error bound. So this is the error of Sn is always less than or equal to, and so I'll put absolute value there, so just in case it's negative. That error will always be less than or equal to this k times b minus a to the fifth, where b minus a is just some associated interval that we're working with here, and then over 180 and then n to the fourth. So what we want in our case is we want 10 to the negative fifth to be our estimation. We have less than or equal to, we're looking for k. Our b and our a are given in our interval. So we have 4 minus 1 raised to the fifth power, and then we have 180 and an n to the fourth. So we need to find k. In order to find k, though, notice you need a fourth derivative. So when we look at that, well, let's keep on looking at derivatives. So for our fourth derivative, first derivative of 1 over x is negative 1 over x squared. Second derivative of x would be positive 2, over x cubed. Third derivative, notice that's x to the negative 3, so that would be negative 6 over x to the fourth. And then fourth derivative, sorry, I'm getting a little ahead of myself, that would be positive 24 over x to the fifth. And notice this function, the 24 over x to the fifth, would be decreasing on the interval 1 to 4. So we have decreasing. So that means we can plug in, so the max is f, the fourth derivative of 1, which would equal, in that case, 24 over 1, or just 24. So since we have 24 as our new value, we have 10 to the negative fifth, or let me write it this way, 1 over 10 to the fifth. is less than or equal to 24 3 to the 5th, 180, and then we have an n to the 4th. Okay. So where can we go from there? Well, we can move the n to the 4th, since that's always going to be a positive. You get n to the 4th is less than or equal to, we'd have 24 3 to the 5th, and then we have a 180 down below, and we have a 10 to the 5th sitting right there. So notice, let's break that apart a little bit. So you have 24, we have a 3 to the 5th, and let's make this 10 to the 4th by reducing this down to 18. Okay, so that means that we can cross off and leave 4 here, and if we divide this by 6, we get a 3 down below, and so this thing equals, you'll cross that off, you'll have 3 to the 4th, so we'd have 4 times 3 to the 4th times 10 to the 4th. Okay, so n to the 4th is less than or equal to 4 times 30 to the 4th power. So that implies that we have n has to be less than or equal to, or did I hit? Now hold on one second here. When I multiply that, my apologies. Oh, okay. I see. My apologies here. We want that error bound to be less than or equal to this. So that's a worst case scenario. So what we wanted, I was wondering what I was doing. So the 10 to the negative 5th, that would be the worst case scenario. So we're flipping this around. My apologies there. So each of these should be flipped around. So we get n greater than or equal to, notice we have the 4th root of 4 times 30 to the 4th. So that should equal the 4th root of 4 times 30. Now, I don't know that one off the top of my head, and I wouldn't make you do that actually off the top of your head either. There's no need to worry there. I'd be fine with this, but there is something to keep in mind. So if you are trying to solve this, and we can try and actually work this out as well, but if you figure out what 4 to the 1/4 power is, and then you multiply that by the 30, you'll get a number that's like 42.42. Right? But what happens is Simpson's rule, since we're talking Simpson's rule in this case for the SN, you have to round up to the next even power. So you need n has to be greater than or equal to, it goes all the way to 44 for your answer. As I said, I wouldn't make you do that unless it's a perfect number where things work out perfectly. We're good to go. But at the end of the day, you need 44 for your actual value because you need to round up to even numbers. So hopefully that makes sense on that piece. All I'm using is what we're using there is just the bounds there. So I see what section were error bounds in. Oh, I definitely need to work on this. Okay, so the error bounds, those occur in the section on approximating your definite integrals. And so I believe that would be, so you do the 4 techniques of integration, and then it would be the 5th section in the integration techniques, I believe, is where you get that. It's right before improper integrals. So you're going to have error bounds for your Simpson's rule, you're going to have error bounds for your trapezoidal rule, you're going to have error bounds for your midpoint rule. Make sure you know those error bounds, and finding a number of, whether it's rectangles or in this case where Simpson's rule uses parabolas or trapezoids, you can find the number of them. Now, the trapezoidal rule uses an even number all the time, and so does Simpson's rule. So those are the only ones you have to kind of watch out for. And in those cases, you'll be able to simplify things a little bit. But that's how we're working with the air bounds. And what that tells us, though, is rather than if we get an integral that we just can't integrate, and we wanted to approximate it within so many decimal points, this is how you do it. You just put in so many estimation points and use the formula for Simpson's rule or trapezoidal rule or midpoint rule, and you'll get there. So that's the nice part about all this, and that's why we need to kind of understand where we're going with that. So, all right. So now we'll move on to area between two curves and kind of get rock and rolling with that. Find the area of the region bounded by y equals e to the x, y equals 12 minus e to the x. Okay, so y equals e to the x. Yeah, and I'm glad to see if you want to practice that stuff, you're more than welcome to shoot me emails and things along those lines. Or as I said, you can stop by office hours and things like that. You're more than welcome to. So this is y equals e to the x. In our next case, we'll draw 12 minus e to the x. So that's reflected it, and then so that would start at -1. So this should be at 11, I believe. So that was 1. This is 11, and so we get something that approaches 12. Kind of closes that on down. And then the area of the region, if we're doing the y-axis, we're looking for this area right here. So this one's not going to be too bad, because notice you have a top function, bottom function, so the only thing we have to figure out is what the heck is that point, right? And so the way to do that, we go y equals e to the x, and then we have y equals 12 minus e to the x. So notice our y values are lined up nicely, so we'll go 12 minus e to the x, and we can figure out our x bound pretty quickly. So if we add e to the x to the other side, you get 12 equals 2 e to the x. And so divide both sides by 2, you get 6 e to the x. Now how do we take care of that? Take a natural log of both sides, so you get a natural log of 6 equals natural log of e to the x. And remember I mentioned before, in before we got cut off the first time, you get x equals, on the right hand side, just by properties of logarithms, and that equals natural log of 6. So our bounds of our integration here, notice where do we start at? We start at 0. Yeah, so that's exactly right. Understanding that x, that's very important. And notice we can start doing the ones with the exponential functions. So this looks scary, but what's our top function? Well, it's the y equals, just by doing our drawing, we have 12 minus e to the x. Okay, so we'll go 12 minus e to the x, and then we have to subtract our bottom function, so that's minus e to the x dx. And simplifying this integral before we integrate this thing, go 0 to natural log of 6. This goes 12 minus 2e to the x. And hopefully this feels a lot better, because our integrals are getting simpler in some regards. As long as you understand how to set that thing up, that was the real trick to this problem. 12x minus 2e to the x, and we have 0 and natural log of 6 going on there. Okay? So moving forward from here, where do we go? Well, that means we get 12 natural log of 6 minus 2e natural log of 6. And then we got to subtract off when we plug in 0. So you get 0 in that first case, minus, but you got to be careful, you get 2e to the 0. That actually does something. Yeah. And so I agree. If you can set this thing up, you're awesome, you're golden, things are good to go. That's exactly right. It's just setting that stuff up. Notice the second component, 2e to the natural log of 6, that's just 2 times 6, essentially. So notice that's 12. So 12 minus an extra 2, so you get 12 natural log of 6, and then minus, so we have 12, and then we got to go, you're going to add that 2 there, so that makes actually 10. So 12 natural log of 6 minus 10. And natural log of 6 is some number greater than 1. So this does make sense because we have a positive value sitting right there. Okay, so hopefully that part makes sense. Setting up is really the key component to a lot of these, I'll be honest with you. Once you get that, life becomes easy. So now our next one, find the volume of the solid where the base is a triangle enclosed by, this thing looks all sorts of crazy. So we have x plus y equals 1. So that means you're going to have this point 1, 0 here, and then you're going to have this point 1, 0 here. And we have a straight line there. And now, what are we going to do? Cross sections perpendicular to the y-axis are being semicircles. Holy mackerel, how the heck does that thing look? So you get a semicircle here, and then you get a semicircle there, and then so this thing kind of shades on in all these different semicircles. So hopefully that makes sense in terms of what's going on. So we have this, the way I'll write this is y equals x plus 1, or we could do, well, not y equals x plus 1. You could do y equals negative x plus 1, or you could do x equals negative y plus 1. We'll have both at our disposal when the time comes. Yeah, so this one is not a torus, so we'll have a little bit more interesting of a problem in terms of what's going on here. So now we got to figure out how in the world do we pick some random element in here and figure out how to write it. Okay, so that's the trick to this. And so notice, I'll actually redraw without those little shapes here. We know it's a semicircle, so we'll deal with that when the time comes. So we got to find, since we're going perpendicular, if we have this distance, we can always find that distance, right? That distance is just x. Or, another way for us to write it, that's negative y plus 1. That might be a little bit better, okay? So x equals negative y plus 1. Now, what do we want to do with that? We want to take 1/2 of that. Right, so we'll take 1/2 of this, and that'll be our radius. So our radius equals 1/2 our negative y plus 1. Okay? And so what we're going to want to do now is an area of a cross section, so area, and now this is in terms of y, equals pi times our radius squared. Well, what's our radius? It's just 1/2 times negative y plus 1, the quantity squared. So this thing looks scary, right? But remember, all we're doing is just taking that little piece, and remember we have a piece right here, and they kind of cross to make, it's kind of like a cone in some regards, just kind of a slanted cone, and only half of it. And now, this would be if it was a full circle, but we only have a half a circle, so we put a half out here and a half out here. So hopefully that makes sense in terms of the areas of the cross section. So when we integrate this thing, what are our bounds on our y? Well, notice our y starting point is 0. We go all the way up to here where y is 1. So 0 to 1. Okay. And now what do we have? Well, we have the 1/2 pi, but notice we're going to square that 1/2 as well. So this is going to be 1/4. And then negative y plus 1 squared will be y squared minus 2y plus 1. So 1/4 times 1/2 makes 1/8 pi. And then we have y squared minus 2y plus 1. This might look kind of scary at first, and we'll see if we're on the right track. So this thing equals 1/8 pi. And then we have, well, the antiderivative of this is going to be 1/3 y cubed minus y squared plus y, evaluated at 1 and 0. So plugging in the the 0 is going to be easy because all those terms will just fall out. So plug in the 1, that's the real interesting part. Notice we get 1/3 minus 1 plus 1. So our final answer to this thing was 1/24 pi. So was the integration difficult? Well, I hope not, right? Because all we were using is just the opposite of the power rule. The real trick to this, I'd say, and what you really need to focus on is being able to come up with those cross-sections. How the heck does this thing look? What's going on there? As soon as you do that, life becomes a ton easier. So really focus on those parts, if anything, when it comes to finding the volumes. So now let's keep it going. Find the volume of the solid obtained by rotating the region enclosed by this x equals 4 or y times the quantity 4 minus y, and then x equals y minus 2 squared about the x-axis. Holy mackerel, what the heck does this thing look like? So, keeping that in mind, I'll draw the two graphs, and I'm actually going to use a couple different colors just to illustrate this. So x equals y minus 2 squared. Notice when you plug in 2 into the y in that case, this is going to be the easier of the two. So you have, when you plug in 2, you're going to get that value, and then all the x values should be positive based off of that. And notice when you plug in 0, you're going to get 4, so I'll even mark that 1, 2, 3, 4. And so we have something like that, 3, 4. So there's one piece, and the other piece, notice we can plug in 0 for y and you get 0, so you'll have 0, 0. And the other part you'll have plug in 4 for y and you'll get 0 as well. So somewhere, and if you plug in numbers in between here, let's see how this thing goes. Plug in a number like 2. Notice you get 2 times 2, which is 4. Oh, what do you know? So you get right there. And so this curve looks something like this. So we're going to take this shape, this crazy shape right here, and revolve it around the x-axis. Holy mackerel, how the heck is this thing going to go? Well, first, let's talk about this a little more in detail. Before we can even go any further, we need to find where these things intersect. So what we'll do is we'll go y minus 2, the quantity squared, equals y times the quantity 4 minus y. So question, are both of those x equals, or is one on the right y? No, they're both x equals, so sorry about that. If you can't see that, I'll put that back in there. So yeah, both of these are x equals. Does that make sense? Sorry, just saw your question. Getting into drawing these things, I get excited. So in this case, notice we have y squared minus 4y plus 4 equals 4y minus y squared. So subtract the 4y over to the other side along with adding the other y squared. Notice you get 2y squared minus 8y plus 4 equals 0. So what does that become? Well, that becomes 2 times the quantity y squared minus 4y plus 2, I believe. If I've done all that correctly, we should be good to go. Alright, so now this isn't going to be pretty, I'll say that. So if we have y and 4 minus y, yeah, we did that, 4y minus y squared. Okay, so now where do we go from here? Well, you use the quadratic formula. Oh yeah, all that thing equals 0. Use the quadratic formula, you get y equals. So we'll have 4 plus or minus the square root of, so we square that term, that b term, minus 4 times a times c. So 4 times 1 times 2 all over 2 times 1. And notice you could leave it as 2, but I factored out the 2, so I'm just using the terms on the inside. So now, where do we go from here? Well, you can write that as the square root of 8, which is 2 times the square root of 2. So this is 4 plus or minus 2 times the square root of 2 all over 2. So holy mackerel, we're left with 2 plus or minus the square root of 2. That's just our bounds, right? So that's what makes this a little bit fun, is seeing how this thing goes from here. Now, what method should we use? What the heck are we doing here to solve this? Well, I would recommend, notice that the functions are already in terms of y. So if that's the case, notice we can take a little shell and revolve that around. That would be my strongest suggestion here. Right, notice I don't have any actually we don't need a trig sub. That's just a bound to our integral, so it's just a nasty integral in terms of our bounds, right? We'll still get an answer, but that's a good idea. Is it a trig sub? No, I think we can avoid it, as a matter of fact. And the big trick, it's one of those cases where the square root doesn't get involved in that. So the real trick is figuring out that distance there, because if you recall, when we use that shell method, so we have something going like this and like this, what we want to do is we want to figure out some random piece and along with that height. So the formula for the shell, you basically take, so I'll write the shell here, you take the circumference, which is 2 pi times the radius times the height. So this is the circumference, and this is the height of the shell. Okay, so this is what makes it kind of crazy, right? What's our radius? Well, that's actually not so bad. It's just going to be our y value, because that's our distance from here to here to some random point. That's just y. So this thing should equal 2 pi y. But now here's where it gets crazy. What is the value of the height of this shell? Well, notice that's, and I'll shade it in here just so you can see it a little bit more. I'll shade it in the black. You get this is your height. So what is that distance? How do we figure it out? Well, this curve is x equals y times 4 minus y. That's our rightmost curve. And then this bottom distance is x equals y minus 2 the quantity squared. And so what we need to do is you go y times 4 minus y. Oops. Y times 4 minus y. And then we got to subtract off the y minus 2 squared. Okay, so this sounds awful, but it's actually not as bad as you think. We actually already did a part of this. So you go 4y minus y squared. Notice it goes minus times the whole quantity, so each one of these you'll have to minus. So you go minus y squared, minus, you'll have a minus 4y, so that becomes a plus 4y. Then we'll go minus a plus 4, and so that'll be minus 4. Okay, so brushing this up in just a second, we can set up the integral. The integral will go from, now you go your bottom bound, that'll be the smaller number, 2 minus square root of 2, to 2 plus square root of 2. Okay. Now, what do we have? We go 2 pi y. And then we got to simplify all that junk that just happened right there. So that goes, we have 4y and another 4y. We have a negative y squared and a negative y squared. So the negative y squared, there's 2 of those. So negative 2y squared. There's 2 4y's, so that makes 8y. And then plus, or in our case, minus 4. And then we have a dy. Okay, so multiplying that on through, let's see if we can solve this within a reasonable distance. 2 minus square root of 2, 2 plus square root of 2. I'll pull the pi out. And then we'll have negative 4y cubed plus 16y squared minus 8y. And then we have a dy. Wowzers, right? So, but we can solve this too. Might not be the prettiest thing we've ever seen, but it'll do the job. So we get pi, antiderivative of the first part is negative y to the fourth. Antiderivative of the second part, you get 16 over 3 y squared, minus our last part would be 16 over 3, that's y cubed in that case. Then minus 4y squared, evaluated at 2 minus square root of 2 and 2 plus square root of 2. Okay, so now moving this forward, you'll get pi times, this will go negative. And I'm not going to try and simplify this, to be honest with you. You get 2 plus square root of 2 to the fourth, and then you get a 2 minus square root of 2 to the fourth, plus 16 thirds, and then we'll go 2 plus square root of 2 cubed minus 2 minus square root of 2 cubed. And then we have a minus 4y squared, so minus 4 times 2 plus square root of 2 squared minus 2 minus square root of 2, the quantity squared. So notice you're going to have a whole bunch of stuff cancel out, but at the end of the day, you're going to have some square roots and some other terms. And I don't want to spend too much time on the numbers, because the numbers, if you had a calculator, you can plug it in and get that actual value. I'm more concerned on the setup of this thing. Right there, right? If you can set this thing up, you're golden. I mean, the rest is just integration and setting up those bounds and all that stuff. Are there questions on that? The different y bounds and all that stuff. I'm just wondering, are there any questions on that piece? So, tricky problem in terms of finding the bounds and all that stuff, because we had a region enclosed, so a little bit different, and wanted to make sure we saw that. Moving forward now, you have find the volume of the solid obtained by rotating the region enclosed. Could we rotate y? Oh, yeah. So if you rotated this thing around the y-axis, it actually becomes a little bit easier. Well, in some regards, because you're actually doing. In that case, I would recommend the disc method or the washer method, and you use your rightmost curve, which is this one. You're going to square that, so it goes pi times that radius squared, then subtract off the pi times this radius squared. So in the other case, if you wanted to see that value, how you actually go about that, so rotate about the y-axis, your radii are going to be just basically taking it all the way. So if I go over to here, that's one function, and I got to subtract off that other component where I just put that hash mark at. So our bounds stay the same. It goes 2 minus root 2, 2 plus root 2. But what we get, r squared, so it's going to be the y times 4 minus y, that quantity squared, minus y minus 2 squared, that quantity squared, and then we're going to take all that and take its antiderivative. So you're going to have a fourth power and things like that, but that's your setup in terms of rotating about the y-axis in that case. Okay, does that make sense in terms of how we did that? It's good to see both methods. That's kind of the tricky part for a lot of this. So yeah, how do you choose between disc, shell, and all that stuff? Well, or washer method. The washer method, the reason why this was washer, because notice you had a difference of 2 curves going on there. The reason why we chose the disc method here, I try and take the path of least resistance. So disc method, because when we're rotating about the y, and we have our functions in terms of y, those are when you use the disc method. So versus the other case, we had our function in terms of y already, and we wanted to rotate about the x. Okay, so that's when you use the shell method, is when they're opposite of what you're rotating about and what the function's in terms of. Doesn't mean we can't try and solve for x. In this case, it would be a little bit harder with the y 4 minus y, but you can always kind of switch it around. And so I can try and illustrate that here too if you need be. But at the end of the day, so this one we're rotating about the x-axis, right? So find the volume obtained from the solid by rotating this region around. I'd highly recommend, if you haven't already caught on, I like drawing the graphs a lot. So there's a reason for that. In this case, if you go 4x minus 4, notice both of these are lines. So one of them is going to have negative 4, and then your x value, where you hit this, will be 1. Not saying that might make much of a difference. Versus the other one, so let me draw that line. So we have those 2 points. This is not to scale whatsoever, by the way. The scaling is not as important as just kind of getting a picture as to where this thing is going. So our other one, we start at 12, and notice we're gonna, when we hit 3 on the x-axis, that's when we're gonna go through. So we're gonna get something that looks like this, and we're enclosing. Holy mackerel! This thing will be all sorts of crazy. Find the volume of the solid. Oh, okay. Let me. I forgot to put one other extra piece here. I knew there was something missing. So, oh yeah, y equals 0. We're good. We're enclosing that in about the x-axis. Oh yeah, the other one I needed here. Sorry about this. I need x equals 0. So there's 2 ways to kind of go about doing this one. We're going about the x-axis, and so notice the region we're enclosing starts right here, and it builds on up. So we have things going like this, and this one's going to be a little bit trickier than usual, and we're rotating this thing this way. So what I'd recommend is, notice you actually have 2 kind of shapes. So this little piece, since we cut it off right here at y equals 0, that's going to cause something special to happen. And then the other curve, notice we have another sort of triangle kind of sitting out here. So when we rotate this thing around, you're going to get this sort of crazy thing happening here, right? And then on top of that, you're going to have this slope down piece that's rotated around as well. So now here's where the images actually come into play. It makes a big difference. So if I'm looking, it looks like the disk method will be the easiest approach. But what is that radius? All right. And so notice our problem point, and I'll put the 1 back in there. That's going to be important. When we go from 0 to 1, notice our top function is negative 4x plus 12. Y equals negative 4x plus 12. So we get pi times, this is our radius, so negative 4x plus 12, whoops. The quantity squared, and then we have a dx. But that's not all of it. Notice that only did up until this circle right here. So the rest, if you look, let me draw it on top again, we have this piece along with this black piece, and we're looking for an intersection point. Notice that integral, for that second piece, it's going to start at 1, and we're going to be rotating that thing around, and the radius that we want, well, notice it's going to be that distance between those 2 curves. So that's going to be a little bit different. And we need to find when negative 4x plus 12 equals the 4x minus 4. Right? So notice, what does that make? That makes, what happens there? So we'll get 8x equals 16. And so x equals 2 is our other bound. So in this case we have a pi, but now here's what we're going to have to do. With that second component, it's like a triangle going in there, and so we have two pieces that we're going to have to consider, and that's actually going to be the washer method. So we're going to take the top one, so that negative 4x plus 12, the quantity squared, and then we're going to subtract off that bottom one. So that would be, in that case, our function is 4x minus 4, the quantity squared. And then we want a dx. Right? So now that's showing you how we can break it up just in terms of what we had here. So now negative 4x plus 12, what does that make? So we get, it's going to be 16x squared. 48 times 2 is 96, I believe. So 96x plus another 144. So when we go over here, notice we still have that 16x squared minus 96x plus 144 sitting on that part. But then we'll have 16x squared minus, so that's 1632. So minus 32x. And then plus 16. Okay, so that means that we can go back and cross out the 16x squareds. Negative 96 plus 32, so that would make negative 64x. 144 minus 16, so that would be 128, so plus 128. Okay, so I think we're ready to rock and roll now. So this is 16x squared, that would be 16 thirds x cubed minus 96 over 2x squared plus 144x evaluated at 0 and 1 plus the integral. So notice now we have negative 64x, that antiderivative will be negative 64 over 2 x squared, and then plus 128x evaluated at 1 and 2, and we need pi times all of this stuff, right? So this is now pi. We'd have 16 thirds, I'm plugging that in, minus 96 over 2, what is that, 48 I believe, minus 48 plus 144. And then we have, that's going to be negative 32, I believe. So negative 32x squared. Ooh, that's going to be a little bit more fun. So we have negative 32, and then we'll have 2 squared, which is 4, minus 1 squared, which is 1, and then plus 128 times 128 times 2 minus 1. Okay. So what does that become? Well, this will be negative 96. And then 128. So that would be, when we take those two, we'll get 32, I believe. So minus 32. This would be 96. And then plus 16 thirds. And then we'll have a pi right there. You don't need to go any further. Actually, you didn't even need to go this far. But hopefully this makes sense in terms of you get pi times, so 16 thirds, I can actually add these together if need be, but plus a 64. So, and that'll do it for us. So you could write it as 3 times 64, and then, yeah, if you wanted to, you could actually simplify it a little bit. So 64, by the way, is 16 times 4. So notice if I multiply that by another 3, I get 12 times 16, and I have another 1 times 16 here. So you'd have pi times 12 times 16, so that'd be 13 times 16, all divided by 3. So, and if you want to do that out, let's see off the top of my head, 13 times 16, so that'd be 160 plus another 48, so that should be, what, 208, I think? Yeah, 208 divided by 3. So 208 pi divided by 3, and that's a final answer. Needless to say, you didn't need to go that far. I'm more concerned on the setup, setting this thing up right there. Now, by the way, we didn't have to go about it that route. You could do using the y bounds, and your life would probably be a lot easier in terms of you're using your rightmost function and your leftmost function. So there will be a little bit of trick to that, but at the end of the day, you can still go about using the shell method, and then you don't have to worry about so many different integration steps. But you'd have to solve for things in terms of x first. So keep that in mind when it comes down to it. Whew. So now, surface area. Uh-oh. So there's different ways to do the surface area depending upon where we're rotating this thing around. So pretend you have some curve. It's going all over the joint, right? And we want to rotate this around. In this case, we're rotating around the x-axis. What we want to do, so we're rotating this thing, and then we get this curve. So ideally, what we need to do, if you have some function f of x, remember this is going to involve that arc length formula. We know that in order to do this, it's going to be same song and dance. We're going to need that arc length formula. So that's going to be the square root, in this case, is a function defined in terms of x, so it's going to be f prime of x, the quantity squared. But in the case when we're revolving around the x-axis, so you have that circumference of the circle going on out there, so that would be the 2 pi, and then in our case we're looking for the y value, which corresponds to f of x. This is the tricky part for a lot of people. So in our case here, notice we have our x bounds. You actually don't need to draw it anymore, but if need be, if you aren't so sure, sine from 0 to pi looks like this. This is y equals sine of x. And so you get kind of this enclosed bowl is what would be happening if we revolve that around the axis there. So what's the surface area of this thing? Don't let your eyes fool you, that's a perfect bowl. Okay, so if that's the case, our bounds, notice we go from 0 to pi. That's not too bad. We can pull the 2 pi out. We have f of x, so that's sine of x. And then we need the square root of, and we'll put the dx out here, but we need f prime of x, or in this case dy dx. Well, notice if the sine is that, the derivative must be cosine of x, and so this is 1 plus cosine of x, the quantity squared. But wait a second, can we deal with that 1 plus cosine squared of x? How do we handle this integral? Any ideas? Is this a substitution in terms of a trig substitution, a u substitution? Is it a is it a trig sub? Well, in some regards, yes. It'll be a couple things. So notice what you have here is if you make a u substitution first, we can make our integral seem a little bit easier. So notice if we had sine squared plus cosine squared theta equals 1, that'd be great, but we don't quite have that in terms of the nice integral. So if we let u first be cosine of x, and then du, we're going to actually do a few substitutions along the way. So du equals negative sine of x dx. Then we have negative du equals sine of x dx. Okay? So that will also change our bounds. And this way we won't have to come back to them later on down the road. I will actually go through changing the bounds just for time's sake in this one. If you wanted to do an antiderivative, a general antiderivative, you can, but it'll be nicer for us to start it off at least by changing the bounds. So the way we change the bounds is you have cosine of 0, and then you have cosine of pi. And notice this sine of x dx, that makes negative du, but we'll have square root of, this becomes 1 plus u squared. And then this is a du, but a negative du. But the beauty here is that this becomes 2 pi, and then you have an integral from 1 to negative 1, which seems kind of backwards, but we have a negative out in there, which we'll talk about in a second. And then this is just square root of 1 plus u squared du. Now, keeping that in mind, where do we go from here? Well, this thing, when you flip the bounds, you can put a negative sign, so a negative and a negative make a positive, so you have 2 pi, an integral from negative 1 to positive 1 of square root of 1 plus u squared du. And now it is ready for that trig substitution. You can actually have done it before. You just let cosine of x equal the tangent of theta. So it's a little bit trickier up there, but you can still do the same song and dance. Now what I'll do, though, we have a 2 pi and all that jazz, so just for simplicity's sake, now that we have a simpler integral, let's just integrate this thing. And this is a trig sub where you can use u equal tangent theta. There actually is another way we could solve this, by the way. If you recognize what shape does that make, you might be able to break through, but it might be hard for you to visualize a little bit. So we can go u equals tangent theta, du equals then secant squared theta, d theta. Actually, I don't think that does. I was thinking minus. My apologies in terms of the shape. So this becomes the square root of 1 plus tan squared theta. And then we have, oh boy, the good old-fashioned secant squared theta d theta. So notice 1 plus tan squared is secant squared. So this whole thing becomes the integral of secant cubed theta d theta. So it's the one everyone loves, right? I don't know if you all remember it, but it's one that pops up over and over again. And in terms of finding a solution to it, it's not horrible if you practice it enough, but you got to just do it over and over and over again. So you're going to use integration by parts. You're going to kind of work through that. And so let's see. We'll try and go through those steps. Yeah, odd power of secant, that's exactly right. So what we'll do is we'll go u equal to secant theta. That means du equals secant theta tangent theta. And so that means dv was secant squared theta, and v equals tangent theta. Sorry for writing small, I'm going to try and fit it all in here. So you have secant theta tangent theta, which is nice. Yeah, so you could try and break it up secant squared minus 1. You'll still get to this roundabout point. You're going to need to use integration by parts. So yeah, you can definitely use secant squared minus 1, or secant squared, and then you can factor secant squared to 1 plus tangent squared. So that's where you're going to have to work with this. But the secant cubed, you're always going to get integration by parts at one step, no matter what your first step is. So I'm just getting to it right away. Not saying you have to do it that way, but it's one of the many. You do it enough times, it'll pop in your head. So this is secant theta, but this is tan squared theta d theta, and that's where the main point is. That tangent squared theta, and that's exactly what Chelsea's mentioned. Now I'll have to use the secant squared theta minus 1. So you get secant cubed theta d theta equals, we have secant theta tangent theta. And notice this is secant squared theta minus 1, right? So when we multiply that, we'll get a minus another integral of secant cubed, theta d theta. And then minus and minus makes plus, so that'll be plus an integral of secant theta d theta. But this integral is the same as the integral on the other side, so this is where we add it over. And that's where you get that 2 times the integral secant cubed theta equals secant theta tangent theta. Then plus this one, I don't know if you remember what it is, but it's one you might want to write down. Same thing with the cosecant. This is natural log of secant theta plus tangent theta. And I can go through that if need be. Just let me know and I'll make some room so we can fit that in there. So now where does this thing go? It's like a holy mackerel moment. So this thing becomes, you can divide both sides by 2, so you get the integral of secant cubed theta, oops, I forgot the d theta there, equals 1/2 times secant theta tangent theta plus the natural log of secant theta plus tangent theta, and plus some c. Oh, and I need all that to be in parentheses. Okay, there we go. But now we aren't done. You have u was equaling tangent theta, so that means if you draw the triangle, tangent theta, so we have theta here, that's u over 1 essentially. So that's the same thing as u over 1. So opposite is here, adjacent is here, so that means this is square root of 1 plus u squared over on the hypotenuse. So this becomes 1/2, the secant theta is square root of 1 plus u squared. The tangent theta was just u. And then we had square root of 1 plus u squared plus tangent theta was just u, and then plus c. But now we're going to have to plug that in over here. So we'll have 2 pi times 1/2. Oh, that was times the whole thing. So we have square root of 1 plus u squared times u plus the natural log of the square root of 1 plus u squared. Plus u. And all this is evaluated at -1 and 1. Now what I just noticed actually after the fact, this is an even integral. So an easier way for me to have written this, we could have written this 4 pi times the integral from 0 to 1 of square root of 1 plus u squared du. So just because you can always double it when you have those bounds being negative to positive on an even integral. So I'm going to change this just to make our lives a little bit easier. Not much, but just a little bit. So this is, I'll plug in 0 there. Notice when I plug in 0 to each of these, I'll get 0 for the first case because I'm multiplying by 0 right there. And then I'll get natural log of, this is 1 plus 0. So natural log of 1 is just 0. So I don't have to worry about that term. So what we're left with is the 4 pi times 1/2 will be 2 pi. And this becomes the square root of 2 times 1, which is just still square root of 2, plus the natural log of the square root of 2 plus 1. Let me write 1 that way. And then we close that off. And we're finally done. I know that wasn't pretty, but it's exactly how we go about it. So the integration, notice we're using those integration techniques over and over again on a lot of these. They can pop up especially on those involving surface area. So, secant cubes, one to kind of write down. I strongly suggest just knowing that integral. It pops up so many times. So now, moving forward to the next piece, we're almost there, the end is near. So, center of mass. How do we actually handle this? Well, there's two formulas that you're going to need to know. Center of mass, you have, well, first off, let me draw this real quick. So if you have 9 minus x squared, and we want to know underneath the graph of the function, so we go 3 and negative 3. And you have something like that. And so we'll shade this in. If things went correctly looking at this, just taking a look, it would seem like we would end up having a nice center of mass at 0, right? Just from the looks of it, for the x coordinate. But we'll see, and I'll show you how we can kind of figure that out. We'll take x bar, and what does that equal? Well, that's 1 over a. Now you could do it with the moments and stuff like that, but it's 1 over a, and then you have an integral a to b of x times f of x dx. And in a similar manner, the y bar for the center of mass is this 1 over a, where a is that area that we just shaded in over there, and it's a to b of 1/2 f of x, the quantity squared, dx. Okay, so those are your formulas for your centroid. Now let's find the center of mass. How do we go about doing that? Well, first off, we're going to need to find this a value. So what does a equal? Well, a equals, notice, oh, I'm sorry, I drew from negative 3 to positive 3, so this won't be quite as easy. My apologies. Be from 0 to 3. So that's a little more fun. Yeah, so the question, do you have to use moments? No, you can avoid that altogether if need be. If you actually simplify the moment equation, so the moment, so first off, what is x bar? X bar is the moment about the y-axis divided by your mass. So this thing equals, just a little FYI, you get the rho that's going on there, times, let me make it an integral, I'll just make that the integral. So you get the rho times the integral of a to b of x, f of x dx. And then what's this value, this m? Well, that's just going to be your rho, which is your density there, so I believe. In terms of that, you get the rho times a to b, or times the integral from a to b of f of x dx. So now what happens? Well, the rho's cancel, and notice this thing right here, that's just a. So notice we've avoided the moments altogether. You can use moments if you want, you're more than welcome to, but you don't need them. So if you just know what the formula is for the centroid, you can be good to go. So sorry, I started with negative 3 to 3. I don't know why I started with negative 3. Oh, I know why. I forgot the interval over the interval 0 to 3. So in terms of this, we actually are going to get an x value. And so our a equals the integral from 0 to 3 of, in our case, it'll be 9 minus our x squared. And then we want dx. So our a value equals, well, this will be 9x minus 1/3 x cubed, evaluated from 0 to 3. So that's equal to 27 minus, this is 1/3 times 27, which is just 9, so that equals 18. So keep that in mind. We'll highlight it over here, a equals 18. Okay, so this is a little side note. Now let's switch up the colors. How do we go about this? Now we'll start with the x bar. So that's going to be 1 over 18 times an integral from a to b, so 0 to 3, x, and we want f of x. Well, what is f of x? It's 9 minus x squared dx. And so notice from here, this is equal to 1 over 18. You have the integral of, from 0 to 3, of 9x minus x cubed dx. So this one won't be pretty. but we will be able to do it nonetheless. So this is 1/18, and then we'll have 9/2 x squared minus 1/4 x to the 4th, and then we evaluate from 0 to 3. So notice this makes 1/18, and this is 81, because 9 times 9 gives you 81 over 2, minus 81, because 3 to the 4th power is 81, over 4. Well, notice you can make this 2 times 81 over 4, and then minus the 81 over 4, so this thing equals 1/18 times a positive 81 over 4. Notice that you have a 9 in common in both of those factors, so this is 2 after you cross off that 9, and so we have 9/8 is our final answer. So we know, and hopefully things will stay in here, so if I did 1, 2, and 3, 9/8, so we'd have something, it's going to be right in this position for our centroid, which is good. That seems reasonable. And so hopefully our centroid lies within the surface, right? Otherwise we got issues. So our next center of mass, we have 1/18. This one should be a little bit nicer in some regards, and well, it depends on how you look at it, I guess. So there's no x to multiply out. We'll have 1/2 f of x, so we get 9 minus x squared, and then we're squaring that thing. Right? But that's not too bad. We just go 81 minus 18x squared, and then plus x to the 4th. Right? And we know all those antiderivatives, so this thing is equal to 1/18, and then we'll have, oh actually, let's pull that 1/2 out in front as well. So we get 1/36, and then we have, so 81, the antiderivative would be 81x, 18x squared, so that would be 18/3 x cubed, so that's 6x cubed, and then 1/5 x to the 5th. Wowzers. So that's going to be a nice one. Evaluated at 0 and 3. So this whole thing equals 1/36 times 81 times 3 is 243. Okay. 6 times x cubed. So that'll be, well, let's write it this way actually. I'll try and make this a little bit nicer. So 81 times 3, I'm going to leave as 3 times 81. And you'll see the method to the madness here. 6 times 27, you can factor out an extra 3 from that, so you can make that 2 times 81. So minus 2 times 81. And then plus 1/5, and then we'd have a 3 times 81. So in other words, we could write that as 3/5 times 81. That'll be a little bit more convenient for us here in a second. So this way we can kind of do it in our head. And the reason why I want you actually to see this value in this case, to make sure it makes sense. So notice 3 times 81 minus 2 times 81, that's 1 times 81, or just 181. Or 1 times 81, I should say. And then 1 plus 3/5 makes 8/5. So you have 8/5. So 1/36 times 8/5 times 81. Okay, so this looks all sorts of nasty right now. But when we actually work this out, you can see the 81 and the 36 share a common factor, so this would be a 9, and this would have a 4 down below. And 9 times 8 is 72, so that'd be 72 over 20. And 72 over 20 can reduce down a little bit more. You can make that 36 over 10, which is probably a good one for us to see. It's 3.6. That's going to be useful. So 36 over 10, which is 3.6. And I'll kind of use that idea. Oh, don't go. Let me come back here. So 3 point. Oh, I did it again. Let me do it this way. So that thing equals just, we'll make it 3.6, just so you can see. So this up here was 9. So 3.6 would be somewhere like right in here if this were to scale. So 3.6, and so our centroid would be right there. So you'd have 9/8, comma 3.6. Okay, hopefully that makes sense. It fits right in there, and it's what we would hope to be the center inside our shape there. So, and notice the question was, do we have to use moments? No, you can avoid it. The moments were used to generate that. Once we find a general formula, we just fixed that, right? The moments were nice, but it wasn't the end-all be-all. It's kind of the underlying theme here. Okay, so for our last problem for the night, I just want to do one physics application. I know you'll be seeing that soon enough and working a little more in detail, but I'll kind of go through one, how it works. So let's say we had a 25-pound rope, and it's 50 feet long and hangs over the edge of a 200-foot building. How much work is done in pulling 10 feet of the rope to the top of the building? How the heck do we do this problem? Well, so let's say we have our building, right? So we have some building sitting here, and that's a beautiful building. We're going to make it a windowless building just to scare the heck out of people, right? So now, up at the top of the building, you have a rope. Okay, and this rope from here to here is 50 feet long. Okay, and that rope weighs 25 pounds. Yeah, oh, I'm glad to hear you like the integration, applying the integration. Yeah, I agree, it is a lot of fun. Especially, you get into the physics problems. I wish we had more time because you can get into a lot of the business applications and things like that. This stuff goes all over the place. But in terms of our time, that's what we just don't have enough time in the class to cover all the topics that we need to. Especially, we're coming up series and sequences. That's going to be an interesting topic, and it has some weird applications that you would never see coming to. So this is our rope, by the way. And when you think about this, we have that 50 feet long, and how much work is done in pulling 10 feet of the rope to the top of the building. So I want you to actually think, and if you have something nearby, if you have like a cord or something, you can hang it off your desk or whatnot, or just try and see what happens as you pull that thing up. And so usually what most people think is that the forces involved are constant, right? So, and the work done is constant. Well, that's not the case here. Think about, as you're pulling more of the rope up, and it's more of it's appearing on top of this building, this stuff will start to coil around and things like that. And so the rope gets lighter. So the amount of work being done on one part of the rope versus the other is going to be different. And so what we do is we break this thing up into a whole bunch of little different intervals. And so, actually, let me use a different color. And so we have this whole idea where we break it up into some small interval, which we'll call delta x for now. And what we need to do is have some defining part for each delta x in terms of how much sort of force is going on. And the way to do that, well, if we can figure out the pounds per foot, then we should be in pretty good shape. And so notice, if we have a 25-pound rope and then a 50-foot rope, the pounds, so let me write over here, the pounds per foot, well, notice you have 25 pounds and then you have 50 feet of rope, so you have 1/2, and let me abbreviate it here, pounds per foot, okay, or just pound per foot. Okay, so now what we need to do is we need to also integrate. That's how we get our work formula going here. So work will equal, in this case, essentially when we take a look at this, what's happening thus far is we get a force. I should write that. Our force would equal 1/2 times our delta x, or which we'll find out as dx, and then force times distance gives us work. And so what is our distance? Well, if we start at 0 and call this 50, and we'll say this distance from here to here is x. So our distance equals x. Okay? So our work equation is force times distance, so we have the 1/2 just times x dx. Now here's the real trick though. What makes this hard for some people is figuring out what are the bounds of integration. And so we're pulling 10 feet of the rope to the top. Okay? So most people say, well, actually I'll let you all figure it out. What do you think the bounds of integration should be? This is, as I said, it's the tricky part for a lot of people. Yeah, so 50 is one of them. We don't want to pull it all the way to from 0 to 50. And I'll explain why. We're only pulling 10 feet of the rope. So we're going to still have a whole bunch of rope hanging over. So our old rope hung all the way down to here. This was 50 feet. We know that this distance here was 10 feet. Right? So all the way down was, oh, let me make markers here. So we had 50 feet down at the bottom, right? What is that marker if we pull 10 feet up? And so now we're starting to coil that stuff up. Yeah, you pull 10 foot of the rope. Oh, let me pull that. I'll hook the battery back up. Yeah, so 40, that's exactly right. So notice our integral, actually, it isn't 0 to 10 is what most people think. The 50 was right on the money. That was spot on, actually. And so where we want to go, it's from 40 to 50, right? Because that's the part that we removed. And so now our integral is actually quite easy. So what we get is, get 1/2, yeah, 1/2, and then it goes 1/2 x squared, evaluated at 40 and 50. And then, so that makes 1/4, and so we'll do 50 squared minus 40 squared, and figure out what that equals. So 50 squared, that'll be 25 with the 2 zeros, and then you'll have 16 with the 2 zeros, right? So that makes 900 divided by 4. Now I don't know much, but I do know you can write this as 9 times 100 divided by 4, and if you take $1, you have 4 quarters essentially, so this is 9 times 25, and so that should be, I believe, 225, and our answer, notice we have feet and we have pounds. The work done is in terms of foot-pounds, so foot-pound. Okay, questions on that? And there's going to be a wide variety of like work problems and things along those lines. The physics problems are left and right in terms of integration. Yeah. So yeah, I thought it'd be more work. That's right. Okay. In terms of the applications, as I said, you're going to see more. And just if you get questions, post them. That's what I'm here for. So just post them in the discussions and whatnot. I apologize for the technical difficulties that we had tonight. Hopefully, though, you were able to learn some stuff and be feeling confident heading into that midterm. So I wish you all the best of luck on the midterm. As I said, if you want to ask some questions, you're more than welcome to stop by during office hours. Or I saw Chelsea mention about the tutoring this week. Please attend that. Or as I said, stop by office hours. All of that works. Just work with the problems heading in. And I wish you all the best of luck. Y'all have a good one.